Okay, I'm starting the recording for our lecture, which is introductory lecture for artificial neural network. Okay, and see, put this thing in presentation mode. Okay, so we are going to discuss the introduction to artificial neural network, which is, by the way, one of the most powerful let's say, building blocks of our artificial intelligence and machine language algorithms. If you look at reinforcement learning, deep learning, it uses neural networks. If you look at generative AI, right, it uses neural networks. So it's very important to all the machine learning algorithms that we are seeing nowadays. Okay, in particular, reinforcement learning and generative AI. Okay, so let's see if I, oh, okay. So we're going to go through definition. Okay, gonna get my pen here. Now, of course, the artificial neural network, it mimics the way our brains work, and the main components are those neural um, nodes, right, that are connected with synapses, right? So in the human brain, you have those neurons connected with synapses, and we mimic those in neural network by having nodes connected with connections, right? So we are just emulating or trying to emulate how the human brain works, okay? And there are multiple types of those neural networks. Okay, we will cover probably one or two. So you have the basic type, which is neural network, and then you have other convolution neural network, RNN, etc., etc. Okay. Um, Now, let's take a look at the basic structure of a neural network. What is composed of? Okay, this is what you see here is the simplest neural network, all right, which is, we call it single layer. Okay, so let's understand where that name came from. Typically, you have inputs, right, to the neural network, and you have outputs. The input can be one or more than one, two, three, a lot. And the output as well can be one output or multiple outputs. And then in between, there are layers. We call them hidden layers because they are between the input and the output. Okay. And how many layers, how many hidden layers you have tells me how many layers in your network. So in this case, we have just one hidden layer, which is this one here. Okay. Now, between the input and the hidden layer, there are these connections, right? And between the hidden layer and the output, there are these connections. These connections they are weighted connections, and we'll see how these computations are evaluated. Weighted connections. So they have weights. All right. And every node here, when it sums all these computations inside it, adds a bias, as we will see very shortly, and then apply a what we call activation function. This is the magic of a neural network. These activation function. Why it is magic? Because these activation functions transforms the computations from linear to nonlinear. You see, linear has a capacity of doing the regression and classification. Nonlinearity surpasses that capacity of linear. Give me an example. Here's what an example. Recall in we did a linear regression, right? and we said we apply these points here, right? And then we had a line in between these points, and we said that this is a linear regression model, right? Now, what about if the points look like this? Okay, let me see. If the points look like this, what about if the points look like something like this? They are all over the place. There are points up, point down. There is no way there is a line that can fit them. So obviously you have some kind of non-linear behavior going on here. Your linear model will not fit them. So you need a non-linear model. Okay. Neural networks are superb, excellent, right? Outstanding in modeling nonlinear behavior. And where is the secret sauce? Activation functions. Okay. All right. Now, okay, so here's an example of a single layer, because I have one hidden layer. This is example of 1, 2, 3, three-layer neural network. If you have more than three, typically the people refer to it as deep neural network, although this definition is loose. Some people want to deep see really many layers, but anyway, you get the idea. We have one or more hidden. Okay, so here's the question. Why would you have one or more hidden layers? Well, obviously, how complex is your system is, how much intelligence you need to have inside this machine. So number of neurons, number of layers typically enables the machine to classify, to model harder problems. Okay. All right. So at the same time, you don't want to have too many layers, too many nodes, right? For simple problem. Well, how do I know I need that much? We have to be expert at these things. You have really to work with these things day in, day out, and then you will start having this knowledge is that this particular type of problem, I need three layers, and in every layer, I need probably 10 nodes. Because the more layers and nodes you add, the more complex computations you have. Okay, so you don't want to have a very complex computation for trivial problem. Okay. Okay, so this is nonlinear behavior model. You can't fit this behavior with a linear regression, right? So you just cannot. Right? You really need a nonlinear model. Okay. The neural network application typically are regression and classification, and they are very related. Regression output is continuous. So for example, if I want this type of problem to be modeled, um, oops, sorry. Okay, if I want this type of data to be modeled with I hope the connection is okay. All right, to be modeled with a neural network machine, then I will see that I care about the output at this point with this value, 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 with this value. This is when I'm interested with a regression output. The output is continuous. But if I'm doing a classification, perhaps I need either here or here. Classify for me, is this student passing the exam or failing the exam? Give me two classes, right? Versus give me continuous. So the regression gives you continuous output, continuous fit, continuous line fit, but classification, no, it gives you discrete values. Okay, pass, fail, car, house, right? What is this image? Is it a car? Is it a house? Okay, so these are the discrete values. Typically, we are interested in classification versus continuous values in regression. Now, obviously, you can convert any regression value to classification. You can assume if I get regression value above 0.5, I'm going to assume it pass. Less than 0.5, I'm going to assume it fail, or a 0, for example. Okay, the magic of a neural network is that they stretch the space. So, for example, let's say I am interested I have points in the red line, and I have points in the blue line, right? I have data points. What am I interested in? I need to classify these 2 points into what? Into points for the blue line points and the points for the red points. Okay, so I need 2 regions. The magic of neural network, it stretches the space, right? It's almost like like a dough. It stretches the space in a way that it makes it easy to classify those. That's what nonlinearity and all these computations of the neural network they kind of بيعجنوا السبيس تبعنا وبيخلوه nice and clean and easy for us to make that clear cut line between the says now these are the red lines and now these are the blue lines. You wouldn't be able to do any non-linear model here. You wouldn't. You cannot. The data is intertwined مع بعض. Okay? All right? Okay, so let's see what the computation of a neural network. The computation of a neural network, it starts from the input all the way to the output. In every layer, let's go back here, in every layer, okay, so let's see here, for example, you have 2 inputs, you have 2 nodes, and you have, let's say, for example, 1 output. You start from the input, right? Every input goes to every internal node in the hidden layer, and this one here as well, right? And this one here as well. You do a computation, and then the output goes to the output node, which sums the output and produce our output. So in every layer, what we do, we take these input data and then multiply it by a weight and send it to the destination node. Okay, so let's zoom in and do some computation. So this is a node here. This is a node, right? And this node is getting data from 3 previous either inputs or 3 previous nodes. Notice that this data here is 2, 3.0 and 1.5. That's my data. And they are in the connection, the connections are weighted, meaning they have weights, meaning I multiply what? The data times the weight. Okay, that's the computation we do. So you multiply 2 times minus 1, 3 times 1.75, 1.5 times 2.0. Then what? Then sum them up. Okay, you can see that this is the result here. Okay. Then after the multiplication of these inputs from the previous layer times the weights and the connections, I do what? Typically, in the node, there is something we call it an offset or a bias. Every node has a bias. Once you are done the computation, you add that bias, a DC value, if you will. Then what? Okay, so you produce a result here. Then that, when you take this result and then you apply it to the activation function. So the nodes does what? It performs the multiplication of weights and inputs. Then it adds a bias. Then it applies what? The activation function. In this case, I have the sigmoid activation function. And the sigmoid activation function has this funny shape, and we'll discuss it later on. But I take whatever output here, which is 1.0, I apply it to the activation function. I get what? 0.73. And that becomes the output of my node, 0.73. Every node has an activation function except the output nodes and the input nodes. They don't have activation functions. Okay? Again, I say that the magic is in the activation function. Why? Because this is when your linear computation becomes non-linear. لأن لاحظ هنا كل اللي بسويه هنا linear. This is linear here. Linear. And linearity has some limit. Okay? Let's see if I have in a second. Okay. That is not going to cut it. Okay, no problem. Okay, now, so here's another example of a node, right? I'm inside this node here, okay? And input, wait on the connection, and wait on the connection, wait on the connection. So these are multiplying the inputs with the connections. And then I get an output here. It looks like my bias here is 0. Then I apply this into my activation function, right? And then my output will be a 1 here. Okay, so this is 1. لاحظ هنا it's approximately a 1 لأنه it's really the answer is 0.9999, so that's why we approximate as 1. Okay, so again, to sum up the node computations, you have data coming from the previous layer. You multiply this data with the weights and the connections. So these connections are weighted. They have weights. Sum, add a bias, get a result, apply it to the activation function, right? And then produce the result for the next layer. Okay, so this is going to the next layer. Now, what are the activation functions that we have? A lot. We have a lot of activation functions. And in this course, we're going to limit ourselves to sigmoid. We'll study later on this one, and a ReLU, this one here. Probably this is as much as we will limit ourselves. We'll see them in the next lecture more in depth. But these are the two activation functions that we'll use mostly in this course. You can see that this sigmoid here, okay. You can see that the value of here, this sigmoid, is between 1 and a 0, right? And around, I'm sorry, yeah, the value of it. Now, around here, anything above, when the input is above, or let's say when the input is positive, then your output is 0.5 and higher, okay? Until you saturate to a 1. Anything negative, as in terms of input, then your output is 0.5 and lower until you become very close to 0. Okay, so and this is because to stimulate the fact that no matter how large the input pulse coming to you from these connections, when you multiply them by the weights, and so you kind of either suppress the signals, these signals, value of a 0, or you take an action, you activate the next layer, value of 1. Okay, so that's what it means. Ignore, take action. You can think of it this way. Okay, the ReLU is this function right here. If your input is negative, your output is 0. If your input is positive, the output is the same as the input. What? Oh, yeah. And oh, by the way, they are one of the most powerful activation functions. لاحظ, if the result of the node computation is negative, when you apply it to ReLU, right, then the result is 0. If the result of the computation is positive, when you apply it to ReLU, the result is itself. So what does that tell you? It tells you that any computations which is below a certain threshold, ignore, make it 0. But positive results, propagate. So you are suppressing negative results. This is very powerful, by the way. This function is very powerful for hardware implementation. If you are implementing neural networks in hardware, So when you do the computation, if you have negative, you just drop it. If you have positive, you just propagate it. So you only need to look at the sign bit. And that's your ReLU function. Okay, so very powerful, very simple to implement. Type. So let's take an example here and say, okay, suppose we have nine data points. Okay, we are trying to, we sampled 9 data points about some employee. And this employee, we plotted the productivity of this employee versus the working hours. Okay, so we find out the productivity of the employee was very low when the working hours were, you know, just 0.1 hour or 0.2. ما لحقش يسوي شيء اصلا. بعدين ولما نشتغل عندنا مثلا خلال 24 ساعه مثلا، لما نشتغل مثلا خلينا نقول 4-5 ساعات او اكثر. See, this is 24, so 0.4 times 24, that will be around 10 hours. Then he is productive or she is productive. Then as the day winds down, this is probably most appropriate. على فكرة الناس اللي بيشتغلوا شفتات طويلة زي الدكاترة probably. As the, you know, you increase more than 12 hours, the productivity of this person drops back to zero almost. تعبان, right? لما يشتغل لك shift 18 و19 و20 و24 ساعة. Okay, so some numbers هلا. So what do we need to do here? Well, we need to, let's see, we need to design a neural network to classify the work as productive and non-productive, okay? Or alternatively, we need to do line fitting, right? We could do either that, okay? We would like a neural network to mimic this behavior. Now, obviously, don't even think about linear regression, because there is no linear regression will fit this data. Don't even think about it. Okay, how do you want to fit the line? It doesn't fit. So you really need nonlinear model like the neural network. Okay, type. So here is, we are proposing this solution. Yeah, we took this to the side, we worked out a network here, and we said, you know what, we have a small network for you. What is it? Well, you have a network of one input. Yeah, because you gave me one input. What's the input? Working hours, right? And then we have one output, the result, right? That curve. Let's see. This is, you need just this productivity number here. So you gave me one input and one output, and therefore my network has one input and one output. Then our expert in neural network in the company created 2 neural nodes, this one and this one. And these neural nodes use what kind of activation function? ReLUs, all right? ReLU activation function. Okay, and the one on the top has a bias or an offset, نفس المعنى, bias or an offset of 9.26, and the bottom one has a bias of or an offset of 1.45. The connections between the input to the input between the input to the nodes has weights minus 33.18 and minus 1.58. And the connections between the hidden layer and the output has weights of what? Minus 0.22 and 1.33. لاحظ, the output node doesn't have any bias, doesn't have any activation function. It just sums in connections that comes to it with the weights. Okay, now, so in this, what we're going to do here, we're going to show you that how we perform the computations and how this model is doing well. So assume that we have this working hours 0.05. يعني يا دوب اشتغل. So I'm assuming the productivity will be less. It's not to, we have, it doesn't go all the way to 1, which is 100%. Okay, so let's evaluate 0.05. So I have here an input of 0.05. Okay, so what do? We multiply this 0.05 with this weight, add the bias, we get a result of 7.6, right? Then we apply it to the what? To the ReLU. ReLU function says if it is negative, 0, positive as is. So you can see that the result of the node, so now you can see that this is all happening inside the node. أو حتى من هنا inside the node. Okay? Now, so let me fix that. Okay, so the boundary of the node really, see if I can get here some color. Can I get the options for color? Maybe not. Okay, no problem. Okay, so the boundary of the node حقيقة is somewhere here. Oops. And okay, somewhere here. This is the boundary of the node, all inside the node. So this is now the output of the node. Okay. Similarly, same computations happen in the bottom node. We have this result here. So now we multiply this result. Gotta fix this. Okay. So this is the node boundary, and then I'll take this result here and I multiply it by the weight for the upper node, and I get this result. I multiply it for the weight for the lower node. Then I sum the results and I get in the output node 0.15. That's the result, which is very similar to what I expect, by the way, right? Why? Because if you look at if you have small number of hours, you should get a small productivity number. Okay. All right. So, okay. So now let's see. If we look in terms of line regression, and let's focus really what happens. If you look at these weights, what they do, right? If you look at these weights, what they do, if you have a positive weight, you are amplified. So for example, let's say, for example, you have data that looks like this. Your input data. So this is the axis here. So your input data, you are increasing it up and down like so. Okay. When you multiply by a negative number, you flip the axis from the other direction. So it becomes something like this. When you multiply by a negative number, right? That negative number changes the value of the x's from the first and third quadrant to the second and fourth, right? That's the effect of multiplying by negative values. And notice that then I send it to this filter here, okay? All right, and this bias. So this curve حقيقة becomes something like, it's almost something like this. If I have two axes here, this curve becomes جاي هيك, almost like this, right? Almost like this. And now what I do is that I keep the positive side of it, and this negative, I make it to a 0. That's in terms of line transformation. I'm trying to show what happens really behind the scene with these weights and biases. Then we multiply this curve by another value. So this negative value. So this get flipped again. And some similar transformation happened with the bottom line. So you end up with this line at the coming from the upper node and this line coming from the lower node. You add the two and you get this shape here. This is really the output. If you vary this x, let's say from 0 all the way to, I don't know what's the maximum value, to 1 or to 24 hours, then you get something like this. And why it's like this? Because the model is trying to fit your data. Didn't you give the model that when there is small value of the working hours and high value of the working hours, the productivity should be around zero? And also at around the middle range, your productivity is maximum. So the line fitting that the model did is trying to satisfy you as much as possible. Now somebody will say, well, wait a minute, but these values are higher here, right? Oh yeah, but we all know that there are errors in the models. صح ولا لا? These are errors. The model, this is the best it could do for you. Okay, so I can make it better fit if I add more layers. Absolutely. Then the question comes, which is better, a model with 2 nodes, does the computation very quickly, or a very accurate model with 2,000 nodes? Well, you have to tell us. Okay, so this is the trade-offs between what and what? Accuracy and complex model, and some kind of an error and a light model. Okay, typically the experts draw the line. They says, well, this is good enough. I'm getting into the diminishing return regions here. I add more layers and more nodes, but I'm getting very small increment. And sometimes you get the adverse effect, by the way. Okay, so there are people who worked with these models for decades, and um, this is why I teach the algorithms of the neural networks to this level. One reason, I am aware that there are libraries out there, whatever tool you use, and you can call up the library, and you can call up you can construct a neural networks in 1 minute, and then you can call up the neural network and say, read the data, train. I am aware of that, but that doesn't make you very understand what happens under the hood, because you have to realize that sometimes you can construct a neural network and it doesn't do what you want. Reason, number of neural nodes, number of layers, activation functions must be appropriate for the function that you are doing. You can't just عشوائي هيك just pull things, and what you have out there are just templates. يعني work most of the times. But you might have an application where you will struggle and you don't know what's going on. Okay? Because these complexities are happening under the hood. You don't know why the model is giving that high error. You just don't know. And the reason is that you are not constructing the right thing. Okay? All right. Now, okay, so this is the line regression. So in general here, let's talk about, you can see here, let's go back here to this point. Yeah, I understand that there is an error here. Okay, we can improve the model. Maybe we change the activation function, we change number of nodes, maybe we add more hidden layers. But if this error is okay for us, then it's okay, right? We don't need to do anything. Okay, now, and then we can always assume, if I want to convert the output from regression output to classification output, I can always say whatever above this line should be what? Should be considered productive. Whatever below this threshold or this line should be non-productive. So now I convert the regression output, which is continuous output, to classification output, which is discrete output. Okay. Now, so in general, any neural network goes through 2 modes of operations. And this is the thought that we leave, probably should stress on it. So this is my model here. My model, the most important of it are those: how many layers, how many inputs, how many outputs, what are the values of the weights, What are the values of the biases? What are the activation functions? That all these questions and answers are my model. So I have to go through what? I construct my neural networks and I have to train it. Train it why? Because you see, recall قبل شوي أنا أعطيتكم هذول الويتس الvalues, these values of the weights, right? This weight value here and this weight value. How did I set those? Through training. Through training. Okay? And people, when you look at generative AI, which does have neural networks, right? It answers you. It answers you because it saves the data. No, it doesn't. What does it save? The weights of the training, the probabilities جواتها هاي الويتس. These models don't save data. الدليل why? If you ask it for a source of the information, it struggles. Oh no. معلش. والله أعطوني lots of data and I can't trace you. And if it gives you, there's a very good chance it's just يلا خذ. You see? These models don't store data. Please keep this in mind. If we want to trace the data to the origin, من نسوي فزلكات هيك زي مثلا الرag model, which is retrieval augmented generation. This is a new fix على فكرة. هو nothing but a fix generative AI, which is neural network. Okay, so these models don't store data. You train them with data to fix these weights and knobs. That's it. Okay, so in the training phase, what we do, okay, in the training phase, we set the W's and the biases. We call them parameters. خلاص خلصنا. We are happy with the accuracy. Then we deploy the model. Okay. When we deploy the model, do we keep training the model? Well, typically you have online, when the model becomes online, you can choose to train the model online, or you can say لا المodel now no training عليه. طبعا okay, so it really depends on how complex your model is, right? So if your model has billions of parameters, يعني كل واحد هسه بده يسألك سؤال بتقول له وقف أنا بدي أخذ يومين تريننج هلا مزبطش. And these are sophisticated models. Okay, GPT stands for what? Generative pre-trained transformer. صح ولا مش صح بعرفش. So it's a pre-trained for you. Okay, so again, back to the question. When I deploy the model to be online, أنا عندي model to detect الجماعة المش كويسين في المطار. بتطلع بصورته البيهيفير تبعه nervous مش nervous. بيعطي alert للسكيورتي. طيب, can this model be trained on as it works? It depends. Some models they are trained, some models they are not. الدكتور خليل سوى بحث وانا كنت معاه co-author السمستر اللي فات, and they worked on a person who sits for a long hours, and then if you feel like your back is aching, right? The small robot tells you do high stretch or اعمل high stretch. What turned out ما فيش stretch بريح البني آدم. what do? You give a feedback للموديل تقول له عارف الحركة اللي راحت هاي ما استفدتش منها. الموديل updates his training data. next time لما تقعد ظهرك يوجعك ما بقول لك سوي هيك لأنه بيعرف إنه ما استفدتش منها. لا خلينا نسوي هيك لعد. ما عارف ولا ارفع ايديك. Okay, so this is when you are online and you continue training, but the model اللي كان عندنا كان simple, not with 8 billion parameters. Okay, so when you deploy a model and to become online, you can continue training, which is in special cases, or you can stop training and serve the public زي اللي بتشوفوه في الchat GPT و its derivatives. Okay, so two modes of operation: training and testing or online. لها أسامي كثيرة. testing online كلها معناها we stop training or we are done training. اوكي طيب كيف done training؟ قبل شوي بتقول لي ممكن يكون لا، هاي بتكون للكستمايزيشن، للبيرسوناليزيشن، للامبروفمنت. اوكي but the main training has been already done. مثال ثاني، الناس اللي if you did you anyone of you saw هاي الماب which self cleans الhouse. So this mob, when it comes in, a robo mob, whatever the name is, it takes about 2 to 3 days to know your house, right? That's what? That's training. That's what? Training. Then it does the job very quickly. Done training. Although it will continue during the online or testing, it will continue update لأنه احنا زحنا الكنباية، فهي لما تتوقع انه هذا المكان فاضي بتيجي بتلاقي if it depends on the algorithm. If it sees it more than one time, it will assume it's stationary, and next time it will avoid it. Okay. Okay, so these are the parameters for neural network. You know, there are plenty, number of layers, how many inputs. طبعا networks, their type of networks. What are the layers? Because some layers they do specialized computations, as we will see ahead. There are different training algorithms. There are metrics. عالم كامل. Okay, it's not easy to with that. If you want to build really sophisticated neural networks, you really need experts for that. It's one thing to have it in a simple assignment and you can try 2 nodes, 3 nodes. Another thing when you have sophisticated neural networks, okay, to perform real complex tasks. Okay, so you really need an expert for that. All right, so here is one thing. There are other values for neural networks, by the way. One of them is to implement what they refer to as encoder decoder. So and this is very very helpful to express. But by the way, this is very useful. But I'm gonna just give a definition of it. So say you really want to you have an input and you want to reconstruct it in a different way. Sounds to me like translation. That's what it sounds. You have a language and you have another language. See, the way you do it, you go through an encoding process, then you go through a decoding process. Okay, so what have we achieved? We represented the input, or we reconstructed the input in a different way. Has many valuable features. I am not sure. Okay, I wish I have time to teach you transformers, which are the backbone of generative AI. But if I do, there's probably a good chance I'm going to knock out from the course reinforcement learning, which is, by the way, very important. So I'm struggling with 2 important topics. So which one I should leave? Okay, there is the replica of a neural network, another application for that. But we're gonna restate back, go back and sum up our lecture, which is right here. Neural network is constructed to mimic the way our brains work. You have input, pulses, input data, which are multiplied by certain weights, summed up inside a node, add to it a bias, and then we apply a nonlinear activation function, right, and send to the next layer. That is the magic of these neural networks, because it turned out we can do wonderful things with this type of computation. The secret sauce, and I keep repeat this, is in the activation function, because they transform the computation from linear to nonlinear. Linearity has its limits. Nonlinear, it allows me to do the space stretching, the wonderful results that we see typically with neural networks. And with that, I conclude my lecture for today. I'm going to take questions from any one of you for this remaining few minutes. Anyone has a question? If I may add, just give me a second, since I discard this, and maybe I turn off, and then I'll take turn off the recording.